So welcome back to our channel once again. In this video we are going to continue with our discussion on the conditions of resonance. Before getting into it, let us have a brief recapitulation of what we have learnt till now. So till now what we have learnt is the first condition of resonance is the relative position of the atom shouldn't change, that is the basic sigma skeleton should remain the same. In that context, I gave you the example of benzene in which you can see the number of sigma bonds here and here are the same, that is the basic sigma skeleton has remained the same. The second condition what we have discussed is total charge on all the resonating structures should also remain the same. That is what has happened in benzene, because in both these cases the species are neutral and the total charge in both these cases are zero, as you can see. We have also learnt a little bit about phenol. The resonance which is happening in this case is from this pi electrons actually move like this from top to middle and from middle to top. That's how you get to these structures. If you haven't seen our previous videos, then I am giving you the link in the description box. Please go to those videos and see how this resonance thing happens in phenol. So that's how we try to draw the resonating structures. As we have seen in the previous videos, we get to see all these resonating structures in all these cases as well. The total charge on these structures, all these structures come as zero. So all these structures are legitimate resonating structures. In today's class, what we are going to discuss is the third condition which is necessary for resonance to happen. That is, these two conditions should be met along with this third one as well. So what is the third condition? The third condition is that the participating orbitals should lie in the same plane or parallel plane. So now this gives rise to a number of questions. Let me explain this in details first. So as we can see, in phenol the resonating structures are something like this, and the resonance was happening like this: top to middle, middle to top, again top to middle and middle to top, again top to middle and middle to top, and so on. So this was what was happening, and this was what was happening in phenol. So now in a molecule like this, what you would expect is you would expect some kind of thing like this, and all these resonating structures should have been present with this extra substitution which was added. So this is something which you expect in a molecule like this as well. But what you see is you don't get to see any resonating structures in this case. So whereas phenol exhibits resonance, this molecule doesn't. Now this gives rise to a number of queries. Let me answer this one by one. So what was happening in phenol? Let us understand what was happening in phenol. If we understand this diagram, then it will be very easy for us to get what was actually happening in phenol. You can understand very well the lone pair of electrons that was actually participating in resonance was actually present in these pi orbitals. Pi orbitals or p orbitals, in these p orbitals. And what was happening was this was going here, this was going here. So what was happening was that this lone pair was being delocalized through all these p orbitals. All these p orbitals. Now one might ask why these are p orbitals. We'll get to those discussions once we learn chemical bonding and all those aspects very well. But as of now, it is sufficient to understand that the p orbitals are actually participating in resonance, and the lone pair of electrons over oxygen that are actually participating in resonance is present over the p orbital present over oxygen atom. So these p electrons are delocalized over all those orbitals present over the carbon atom. Now if we can understand that this, if you consider this benzene ring and this OH to be in the plane of this notebook, you can understand that the p orbitals are actually perpendicular to this plane. are actually somewhere here, are actually perpendicular to the plane of this notebook. So if this is the plane of this benzene ring along with this OH, then the p orbitals are actually somewhere like this. It is somewhat like this, one above the plane and one below the plane. So what you can understand from this is, so the p orbitals are actually in a plane which is perpendicular to this plane, So it is present in a plane like this. There are number of planes, means these two orbitals are present in this plane and these two orbitals are present in a different plane, these two orbitals are present in a different plane, but all these planes are actually perpendicular to the plane of this benzene ring. That is, all this orbital and this orbital is lying in a plane like this, which is perpendicular to the plane containing the benzene ring. These two are present in a different plane which is again perpendicular to the plane containing this benzene ring, and this is again perpendicular to that plane containing the same benzene ring. But what is more important is that all these three planes what we have considered for these p orbitals are actually perpendicular to this plane containing the benzene ring, but these three planes are actually parallel to each other. So these planes are parallel to each other, although they are perpendicular to this plane, but they are parallel to each other. So what we can say is that all the orbitals are actually residing in parallel planes. The orbitals which are taking part in resonance are actually in parallel planes. They might be perpendicular to the plane containing the benzene ring, but they are in parallel planes with respect to each other. The p orbitals are in parallel planes. That's what I am trying to say. Let me repeat this once again. The p orbitals are present in a plane parallel to the plane containing the benzene ring along with that O and H atom. So these planes are parallel to each other, and these are the orbitals which actually participate in this resonance. So now you can understand, if suppose the molecule we have taken is this, where we said that there will be no resonance. So we took a molecule like this and said that there will be no resonance. What is happening in a molecule like this is, actually because of the presence of this bulky group, this bulky alkyl group, that is bigger sized alkyl groups, because of steric repulsion, this will tend to rotate. And if this tends to rotate, now you can understand, if this tends to rotate, if this rotates, then this p orbital will also rotate, and it will suppose come in a position somewhat like this. Now you can see this orbital is not a parallel orbital with these orbitals, with these p orbitals. Understood? So these p orbitals are still parallel to each other, these orbitals are parallel to each other, but the p orbital of oxygen atom which was taking part in resonance has now tilted a little bit, and so it has now moved on to a different plane which is not parallel to these planes containing the other p orbitals. So once this happens, the p orbital goes to a different plane, it is not going to, this p orbital is not going to take part in resonance anymore. So this kind of thing, top to middle and middle to top, is something you are not going to see in a molecule like this. Understood? Now the question is, what is the experimental evidence of this? You are saying that resonance is not going to occur in a molecule like this, whereas resonance is going to occur in a molecule like this. So whatever it is, it has to be experimentally verified. Now let us say the experimental backing behind this. So in a molecule like this, that is phenol, we said resonance is going to happen. So this top to middle and middle to top transition is going to happen. So you are going to end up with the structures like this, and so on. And so on, the final structure is going to look like this. So as you can understand, out of these 5 resonating structures, 2 I haven't drawn. There are three structures where there are C double bond O. There are 3 structures where there are C double bond O, and there are 2 structures where there is a C single bond O. So if you take the resonant hybrid, which is being represented like this, as I have shown for benzene, for phenol it is going to look somewhat like this. It is going to look somewhat like this, and what you are going to show is this negative, and this negative, because the negative charges, as you can see from the resonating structures, are only going to come at the ortho and the para positions. You can see the next resonating structure is going to look somewhat like this, and you are going to draw it like this. So what we say is, you draw a positive charge over here and you draw something like this. This actually indicates this is the resonant hybrid. Remember, this is the resonant hybrid. So this actually means that the negative charges reside either in the ortho positions or in the para positions. Now if you take phenol in a beaker like this and try to measure the experimental bond length. So what you are doing, you are taking phenol in this beaker. So understand one more thing that I have cleared in the last video itself, that once you are taking phenol in it, remember that you are actually taking the resonant hybrid. You cannot separate the resonating structures experimentally. So what you are ideally taking is the resonant hybrid, which is the average of all these resonating structures. So any experimental property you determine is actually the experimental property of the resonant hybrid, which means that all the properties, the individual properties of all of this will be shown in the property of this resonant hybrid. So in this case, what we are going to determine is, we are going to determine the CO bond length. The CO bond length. So what do we expect? Out of these 5 resonating structures, if you see, 2 of these resonating structures has a C single bond O, whereas 3 of them has a C double bond O. So what do we expect? We expect a bond length in between a C single bond O and a C double bond O, because both this C single bond O and C double bond O is present in all the structures out of this. So we do expect a bond length in between a C single bond O and a C double bond O, and that's what we actually get. What does this mean? This observation simply means that in phenol a resonance like this is actually happening. It's because of this kind of resonance only that this bond is acquiring a double bond nature. This one is acquiring a double bond nature. If this wouldn't have happened, then this wouldn't have acquired a double bond nature. That means that yes, resonance is happening in a system like phenol. But whenever you take a system like this and perform the same experiment, that is, you try to determine the experimental bond length, the experimental CO bond length, what you end up with is a clean C single bond O bond length. You don't get a bond length in between C single bond O and C double bond O. What does that suggest? That again suggests that this kind of top to middle and middle to top thing is not happening in a system like this. That is, this thing is hindered. If this is hindered, these resonating structures cannot be formed, and since they cannot be formed, so there will be no double bond O character in any one of the resonating structures. So you are going to end up with a C single bond O bond length only. That's how we actually experimentally try to say that yes, resonance is happening in a system like this, whereas it is not happening in a system like this where there are 2 bulky substituents at the ortho positions. Now let us go to the next one. So this is one more example. This is the example of nitrobenzene. How does resonance happen in a system like this? Let us understand how resonance in a system like this happens. So in this case, you can understand that this can move. This middle to middle migration can happen. Since this is a bond to bond migration, so this is middle to middle, and since this is a bond to atom migration, so this is middle to top. So that's how we get a structure like this. Now what can happen is this can go here and we end up with a structure like this. And again, this and these are same. I mistakenly have drawn it. So in the next structure, what is going to happen is this bond is going to migrate here, and you get a positive charge over here because this bond migrates. Once the bond migrates, the electrons also migrate with the bond. So this now will definitely acquire a positive charge, and this positive charge gets neutralized since these two electrons from this position has shifted over here. In the next thing, what happens is this is going to shift here and this is going to shift here, and you are going to end up with a structure like this. Other than this, what can happen? One more thing can happen here as well. That is, if you write it like this, you can understand this kind of thing can happen, top to middle and middle to top. This kind of thing can happen which does not involve the benzene ring itself. So this kind of thing can happen. Now the thing is, resonance happens in a system like this. We understand this. Resonance is going to happen in a system like this. What is the experimental background? Again, if you try and measure the experimental CN bond length for this molecule, you are actually taking the resonant hybrid, mind it. So what you are going to end up with is a bond length between C single bond end and the C double bond end, indicating that a resonance like this is definitely happening. That's why double bond character is being acquired by some of the resonating structures. That's why we end up with an experimental observation like this. That's why it happens like this. Now, if you take a molecule like this, we take a bromo substitution over here. Let me clear the board for you, otherwise it would be a little difficult for you to understand. So now if you take a molecule like this, where there is a simple bromo substitution at the ortho position, because of this bulkier sized bromine atoms, this will again rotate, and once it rotates, these pi orbitals or these p orbitals is not going to remain in same plane with these p orbitals, and that's why resonance is not going to happen in a system like this. And what's the experimental evidence? Again, the experimental evidence is you take a molecule like this and measure the CN bond length. You measure the CN bond length, you are going to end up with a clean C single bond end bond length. You are not going to get anything between a C single bond end and a C double bond end, because none of the resonating structures is going to acquire this double bond which arises because of this kind of shift. Since this kind of shift is completely inhibited because of this steric bulkness of this bromine atom, we call it steric inhibition of resonance. That's why we are not going to get any double bond character over here, and that's why a pure single C single bond end nature is going to be observed in this case of bromo substituted nitrobenzene. So now let us look into some other examples as well. In this case of aniline, we have studied earlier that yes, resonance can happen. Resonance actually happens like this and so on. But in these two cases, if you substitute this bulky group in the ortho positions, you can understand pretty well that these bulky groups is going to again turn this like this, and resonance is not going to happen because the involved orbitals in this case as well are not in parallel planes. In this case, it's because of the substitution of this over here and this over here that is going to create a steric bulkness, and to relieve that, this is going to move. In order to relieve the steric bulkness, this is going to move, and that's why the involved p orbitals will again not be in the same plane. That's why you are going to end up with a bond length which equals to C single bond end. Nothing in between C single bond end and C double bond end you are going to obtain. But if you suppose you are taking this molecule, you are taking nitrobenzene, and you are measuring the, please listen to this because this is going to be very interesting. So you are taking this molecule and suppose you are measuring the NO bond length, what do you expect? Even if in this case, suppose in this case, this kind of thing is happening, this top to middle and middle to top is happening, so you are going to end up something in between n single bond O and n double bond O. Now in this case where there is a bromo substitution, if you measure the NO bond length, what do you expect and what you are going to end up with? Remember this thing is prohibited. This thing is prohibited because this has moved. But although this has moved, this has moved means this orbital over p has moved and this orbital over p has moved, and both of them has been moved to the same extent. That is, now the position of this orbital is something like this, and the position of this orbital is also something like this. Now these two are again in parallel planes. So although you are not going to get this, if there is a bromo substitution you are not going to get this, but this kind of resonance can never be prohibited because even if they have moved, they are still in parallel planes. So if you measure the NO bond lengths in this case as well, you are going to end up with something in between a n single bond O and n double bond O. Please let us know if you have found any difficulties in understanding this. This kind of resonance is prohibited, but this kind of resonance is still not prohibited because even if they have moved, they are still in parallel planes. Okay, the new positions are also such that they are parallel to each other. That is, the new position of O is now something like this, and the new position of that double bond O is something like this. Now if n is like this, if you draw it like this, even if it has moved, these are still, this has also moved, so these are still in parallel planes with respect to each other. So there is no problem or harm in a resonance like this. I believe you have understood it. Now let's go to some more examples. Up to now what we have studied is resonance in a system like this, where pi electron was delocalizing with the help of a sigma bridge. The example was benzene. In the second case, what we have looked onto is the delocalization of lone pair of electrons taking assistance from a sigma bridge. In the third example, what we have studied, or what we are going to study today, is the delocalization of a negative charge taking assistance of a sigma bridge. Now let us take phenolate. We were taking phenol up to now. Now let us take the example of phenolate. So what happens in a molecule like this? Now you understand this negative charge means again p electrons or pi electrons. This is going to delocalize. How is it going to delocalize? This is simply going to shift like this, top to middle and middle to top. You get up something like this. Now this will again migrate. You get something like this. This will again migrate. You get something like this, and the final resonating structure will look somewhat like this. It's the same protocol of top to middle and middle to top what we have followed. We have seen where there is pi electrons and we have tried to delocalize the pi electrons itself. Now in the fourth kind of example, what we are going to study is the delocalization of positive charge. Now you need to understand, if it is a positive charge, suppose in the molecule what we have taken is this is known as a benzyl carbocation. So what happens in a system like this? Now if you try to do this top to middle and middle to top, you understand you can only delocalize pi electrons, delocalize negative charges or delocalize electrons. This is a positive charge. Positive charge means there is a dearth of electrons. This carbon is actually facing a dearth of electrons. It doesn't have extra electrons to take part in migration. Now in this case what will happen? This has now a vacant orbital that has to be fulfilled in order to diminish the positive charge density over here. Remember, in the very first video I have told you need to diminish your charges, you need to distribute your charges. Whatever the charge might be, positive or negative charge, nothing is good. You need to delocalize it in order to get stabilized. So how how will this dearth of electrons be fulfilled? This is going to be fulfilled like this. The pi electrons over here is going to shift like this. This is middle to middle transition, since this is a bond to bond migration. So you are going to end up with this, and a positive charge over here because the bond here along with its electrons has migrated. So you are going to get something like this. Now in the third resonating structure, this middle to middle transition is going to take place. You are going to get something like this. In the fourth one, you are going to get something like this, where this has shifted along with its pi electrons, so you get a positive charge over here. Here we haven't shown the last resonating structure, that is something like what? Like this. Okay, I believe this is clear to you. The delocalization of positive charges. Positive charges cannot delocalize like this because these are not extra electrons. These are not electrons that can delocalize. Instead, these actually has an orbital which doesn't have electrons, and it needs electrons to actually diminish this positive charge over here. Where will it get its electrons from? It is going to get its electrons from the nearest pi bond that is present over here, and since this is a bond to bond migration, this will happen like this. That's what has been showed here. So thank you for watching this. If you have liked the video, please do share and subscribe to the channel.